All right, welcome back. So in the previous example, we talked about translations, reflections, rotations, and dilations. But now we're just going to talk about the specifics of each. So with a translation, these are all transformations. Transformations are basically you have a shape and then that shape moves. It transforms into something else. And there's 4 different ones that we've discussed so far. So for a translation, there's a rule. You start with a point. This arrow means that it transforms. And this A and this B this is talking about the horizontal shift. Okay, so if you added A or you added a number, if you added 2, you would be shifting 2 units to the right in the positive direction. If you subtracted 2, you'd be moving 2 units to the left in the negative direction. For the Y, if you add a number and it's a positive number, then you're going to be shifting up. And if it's a negative number, then you're going to be shifting down. So that's what this rule states. This rule, it tells you exactly what the actual shift is horizontally and vertically. The next is a reflection, and here are the 2 rules. Reflections have 2 rules that we're going to discuss, and if you notice, we start with a point, and then what happens? Well, the X and the Y stay in the same place, but what happens is a negative occurs. And when you have a negative recur in the X part, so you have a point, and only the X part becomes negative, think about that. What would that be? What would that look like? So if I have a point like this, and then I have a point over here, right, that has X, Y, and then the X becomes negative, well, that would mean it would shift over here, right, and it would become negative X, Y. And so what that is that is a reflection across the Y axis. So sometimes I just like to draw little points out and it helps me remember what's going on. And then if we have this one right here, so XY goes to what happens here, the X, but the negative becomes Y. Well, here we have a different X-axis, right? And we have our same point, XY. But now the Y becomes negative, but the X stays the same. So if the X stays the same, but the Y becomes negative, that means it's going to be down here, right? So this rule represents a reflection across the X-axis. So this rule is a reflection across the X-axis. So these should all be on flashcards. This is going to, you need to memorize these. Okay, so let's put our little flashcard note here on the side. All right, look at this next one. Now this one's fun. This is a rotation. Now, when I look at rotation, what I think is funny is we have X, Y is in this particular order, but then what happens? The place of X and Y rotates. Do you see that? The X is first now the X is second, and the Y is second, and now it's first. So the places are actually rotating. And so when it rotates in this is a rotation about the 0, 0, 0, the center, and it's 90 degrees clockwise. So if I was to look at this one I think is better if we actually call XY a point. So let's say I call it 1, 2. So I have 1, 2, and that's my point. And then it rotates, which means the Y becomes 2, and then this becomes negative. So, is that right? Did I do that right? Yeah. Okay. So then what happens? 2 1, 2, negative 1, then that same point, you're here, and then it rotates down here. Okay? So it's a rotation. This is going in the clockwise. That's how you get this clockwise right here. That's going in the clockwise direction. It's going here, and it's going kind of like around the clock. Okay, so that's the rule for that one. If we look at the next one here, I would have a point. Let's say I have a point, what was it, 1, 2 again. And then that's going to rotate to negative 2, 1. Okay, so if I have 1, 2, so here's 1, 2. And then it rotates into negative 2, 1, 2, positive 1. Well, now my point is rotating this way, which would be a rotation about 0, 0, 90 degrees counterclockwise. So this is going in the counterclockwise direction. All right? So you just really, really need to memorize these rules. This is rotation about 90 degrees counterclockwise. And lastly, there's this one here. I'll do a little thing right here. And if I have a point, right, we'll call our point 1, 2. Let's see what happens. 1, 2. And then it becomes, okay, so they don't rotate. They just both become negative. Negative 1, negative 2. That would be negative 1 would be here, and then negative 2 would be here. And so this is just a full-on 180 degrees rotation. So that is the rule for that. Okay, and then lastly, there are dilations, and we talked about dilations in the rule. And basically, if the rule, as long as it's bigger than 0, this is a dilation, which means it can either get bigger or smaller with center 0, 0 and scale factor k. So anything where they have that number, the same number just written in front of the x and the y, you automatically know it's the dilation, which is super nice. Okay. So, more vocabulary. An isometry is a transformation, so that means one of these, that preserves length, angle measure, and area. So this is an isometry where the transformation preserves, that means it stays the same. So what the transformation preserves the length, angle measures, and area. So it's basically, there is a figure, it moves, and it stays the same size. Because of these properties, an isometry produces an image that is congruent to the pre-image. So the image is congruent to the pre-image. So an isometry is a type of transformation that preserves the length, angle measure, and area. And because of all that, the image, what you start with is congruent to the pre-image. Now this is really, really super important because in chapter 4 is all about congruence. And for the most part, we're going to be talking about triangles being congruent. And we're going to talk about all these different ways in chapter 4 how you can tell basically triangles are congruent. But for the first bit, we're going to throw some quadrilaterals in there as well. But the first way that we're going to tell whether something is congruent or not is by looking at the transformation. So which of these transformations does the size stay the same? Well, it stays the same with translations, right? Because you have the same image and it just shifts. So the image is the same. It stays the same with a reflection, right? Because you have the same image, it just flips over one way or the other. It stays the same with a rotation because you have the same image, it just moves, it rotates around the circle. Does it stay the same with a dilation? No, a dilation, you have it and then it gets bigger, or you have it and it gets smaller. That's what a dilation is. So because of that, figures that are dilations are not congruent. Okay, so anything that has this rule and you know there's a number in front, you know it's a dilation, and dilation are not congruent to each other. However, you know that translations, reflections, and rotations they can provide congruence. If you have an image and it's translated, well, those two images are congruent. If you have an image and it's reflected, those two images are congruent. If you have an image and it's rotated, those two images are congruent. If you have an image and it's dilated, no, not congruent. It's either going to be bigger or smaller. So these are the isometries. So isometries can be number 1, translations. Number 2, reflections. And number 3, rotations. Okay. Another vocabulary term, a rigid transformation, is just another name for an isometry. A rigid transformation, another name for isometry, basically a transformation that preserves length, angle, measure, and area. Okay, the pre-image and the image are congruent to each other. All right, let's look at some problems on how this is all worked out. So, this states that translations, reflections, and rotations produce images that are congruent, woohoo, to their pre-image, okay? However, dilations with scale factor not equaling to 1 produce images that are not congruent. So dilations, not congruent, okay, to their pre-images. So let's look at some examples. So example 2 states, determine whether figures are congruent. Determine whether the polygons with the given vertices, A, B, C, so we have right here A, B, C, is congruent to P, Q, R. What do you think? Do you think that these two figures are congruent to each other? Think about it. Okay, so what we'd have to see is, what does this look like? This to me looks like it could be, does it look like a translation, a reflection, a rotation, a dilation? This to me looks like it could be a translation, because if you take this right here and you look at P, right, it moves over to the left 1 and then down 1, 2, 3. Okay, let's look at B and Q. Goes over to the left 1 and then down 1, 2, 3. Oh, that's the same rule. Okay, what about from C to R? Goes over to the left 1 and then down 1, 2, 3. So there you have it. This is a translation. We're starting here with our pre-image and ending up here. So what we can say is the triangles, because this is a translation, the triangles are congruent. So you could say that like this. You could say triangle ABC is congruent to triangle PQR. Okay, now we just need to state why. These are congruent because triangle ABC can be mapped to triangle PQR by a translation, which is XY. And then what was the rule? What happened? We went to, the X part went to the left 1, so that would be X minus 1. And then it went, what, down 1, 2, 3. So that would be Y minus 3. So that would be the rule. So therefore, the triangles are congruent because it is a transformation that is a translation. So that means it is an isometry. All right, let's look at this next example here. B. What's going on? So we're starting here with A, B, and C, right? A, B, C. And then what's happening is ending up with the image PQR? What's happening with ABC and PQR? Is it a translation? Is it reflection, rotation, or dilation? What do you think? Well, to me, if you're looking at this figure, it looks kind of small and then it gets bigger. And the only thing that can be is a dilation. So since it's a dilation, remember that is the one thing that is not congruent. So it's saying determine whether the polygons with the given vertices are congruent. So what we would say is that the triangles are not congruent. Okay, you can state that like this: ABC, triangle ABC. You can make a congruent sign and then you put a line through it, and that means not congruent. Is not congruent to triangle PQR. Okay, so those two triangles aren't congruent because triangle ABC can be mapped to triangle PQR by a dilation, and then we just need to figure out what that scale factor is. So basically, you know, if we have 2 is A is turning into P, so 2 times something is 3, right? And so sometimes what I like to do is we can just set up an equation, right? So we know we take this, we multiply it by the scale factor, and we end up with this. So if we take that x value, like a way to figure out the scale factor, sometimes it's easy and obvious that this one isn't. So we're going to take this number 2, and we know that we multiply 2 by that scale number, and we get 3. And so this is just a super easy way to figure out what the scale factor is, right? Because that's what the rule is for dilations. You take this vertice, multiply it by k, and you get that. So 2, the x value, times k equals 3. Then we just get k by itself. So we set up our little equation. We divide both sides by 2 to get k by itself, and we end up with 3/2. And then we say, okay, does that same thing happen for the y value? So if I take -2 and I multiply it by this scale factor, I should get -3. Does that happen? So if I take -2 and I multiply it by the scale factor of 3/2, well, what's going to happen? Well, we're going to look to cross cancel, right, by multiplying these fractions. Those 2's are going to cancel out and become 1, and then we multiply across, and we end up with a negative times 3, which is -3/1, which is just -3. And if you start with -2, you multiply it by 3/2, you end up with -3, which is exactly what they have here. So we might want to try it over here just to make sure with B and Q, to make sure that we have that same K value one more time. So that means if I take this pre-image, I multiply it by the scale factor of 3/2, I should get this 6. So 4 multiplied by 3/2, I should get 6. Let's see. 4 times 3/2, right? So I'm multiplying fractions. I'm going to look to cross cancel. Between 4 and 2, there's a common factor of 2. 2 goes into 2 one time. 2 goes into 4 2 times. And then I multiply across. 2 times 3 is 6/1, which is just 6. And so when I start by 4, I multiply by the scale factor. I do get 6, so that's right. And then we already did -2 and -3 there, so we know that that's right as well. So yes, that's the scale factor. So ABC can be mapped to triangle ABC can be mapped to triangle PQR by a dilation with scale factor 3/2, and the rule is xy goes to 3/2x, 3/2y. That would be the dilation. All right, perfect. Now let's go ahead and check it out, example 2. So we're going to determine whether the polygons with the given vertices are congruent, and then support our answer by describing the transformation. Okay, so we have A, B, and C. We're going to go ahead and plot those first. So we have 2, -1. That's A. We have B, which is 3, 0, B. And C, which is 2, 3, 1, 2, 3. C. Okay, and then that maps to P, which is 1, 2, P, Q, 0, 3, and R, -3, 1, 2, 3, up to 1, 2. And we get this figure here. Okay, so we're starting here, and then it's moving over here. So this right here, we plotted it. We want to figure out, okay, is this a translation? Is it a reflection? Is it a rotation? Or is it a dilation? What do you guys think? Well, to me, it doesn't really look like this figure is getting bigger. It looks like it stays the same size, right? So it doesn't look like it is a translation because where the shape is, it's just totally moving. So this definitely, it doesn't look like a reflection. This looks like a rotation, right? And it looks like it's rotating this way, counterclockwise. Do you guys remember what that rule is for a counterclockwise rotation? Counterclockwise, well, let's see, look at B. What are the values of B? B is 3, 0, and then what's happening? It is rotating to Q, which is 0, 3. So you see those X and Y, they're rotating, right? So this is, we know that this is a rotation, so we know that since it's a rotation, it's either, that means that the triangles are congruent. So we can say triangle ABC is congruent to triangle PQR. Okay? Because triangle ABC can be mapped to triangle PQR by a rotation of, we start with XY. We know that the X and the Y, they're going to get rotated, right? And we know that one of them's going to, ooh, that's not rotated. Where's my friend? Correction tape. Correction tape, you are so nice to me. You are my friend. Okay, so they get rotated. So the Y, ooh, that was not my friend. Smudges, you are not my friend. Okay, here we go. It gets rotated. So this is Y and this is X. But we know that one of them's negative. And so, you know, we have those rules and we need to memorize them, right? But let me look at this. Let me see what's happening here. Let's see if we can kind of use logic through it. So this point A is 2, -1, and that is transforming up here to P, which is 1, 2. So we're starting here, and the Y is rotating, the X is rotating, but this, which was negative, is now becoming positive, which means that this is a negative Y. Okay? So, and if we remember, this is moving counterclockwise, and our rule right here says XY becomes -YX. That's a rotation about 0, 0, 90 degrees counterclockwise rotation. And that's the rule. And you can really see that 90 degrees. You can see it here with B and Q because there's a 90-degree angle when you connect it to the origin. Also, you can see that same thing if we connect, what are the points that we just found, A to the origin. You connect A to the origin and P to the origin. You see how you can see that 90-degree angle there? And so, yes, A is rotating counterclockwise 90 degrees to P right there. And the same is true with B rotating to Q and C rotating to R. They're all 90-degree rotations counterclockwise, and this is the rule for that. So there is the answer. So this is how, for these problems, you show your work, and that's the response you would write to answer the question whether the two triangles are congruent. Yes, so they're congruent because they're a rotation. They would be congruent if we had, what do we have up here? A translation. And we didn't have an example of a reflection, but if there was a reflection, those would also be congruent. However, if you have a shape like this and it changes the size and becomes either bigger or smaller and it's a dilation, the figures are not congruent. All right, that's it for example 2. I'll see you in a little bit for example 3.